Section 2.1 is about tangent lines and velocity, and we are going to see a connection between the two as we work. So to start with, we're going to actually encounter something that we've seen before, and that is the idea of secant and tangent lines. So do you remember what the difference is between secant and tangent lines? What is a secant line? Right, it crosses through a graph at 2 points, and so I'm going to draw a graph, and there's nothing special about me drawing this particular one. I'm going to draw it as a parabola. And a secant line might look something like this, right? It's intentionally going through two locations on the curve. And then what about a tangent line then? Right, it touches the graph in exactly one location, and that's sort of not exactly accurate either. It actually could cross the graph again at another point. Like, let's say, for instance, you don't need to draw this, but let's say, for instance, the graph does something like that. Then it is possible that if we drew a tangent line so that it touched it at this point right here, that it actually crosses through the graph later on. That crossing through the graph later on doesn't prevent that from actually being a tangent line. The issue with tangent line is simply that it touches through that graph nearby in exactly one place. Is that okay with you guys? I mean, like, we actually have the possibility of a tangent line somewhere further out doing this, and but that's not a problem. Now, I haven't actually told you exactly how we draw these tangent lines. We'll get there in a minute. But the first thing I want you to take a look at is if we were going to be talking about finding the slope of these lines, then we find slope by looking at the change in y over the change in x. And we did this way back in section 1.1, right, with actual numerical values. We did this. So I want you to take a look at the secant line idea. If this point over here on the secant line were the ordered pair a, f of a, right, so this is the x value of a, and this is the y value of f of a. And then we went from this x value over to this x value, and the distance between them was h. So we just added h to the number x. Then what would happen is that this point over here would be the point x plus h, not x, we used a plus h, sorry. And then the corresponding y value, which is f of a plus h. Okay, so we have 2 points. We have 2 ordered pairs. And if we actually were to find then the slope, we would actually need to take the y values and subtract them. Well, the first y value, or the second y value over here, f of a plus h, is written right here, minus the first y value, which was f of a, over here. So we subtracted the y values. And then we subtracted the x values. So the second x value is a plus h, right here. And we would subtract the first x value, which was a. And that's on bottom down here. So we have a plus h minus a. If we simplify this denominator, we simply leave ourselves with h in the denominator. Okay, so does everybody see where that quantity came from? You might have seen this done in algebra before. Do you remember the name that was given to this quantity in algebra? Does anybody remember it? It's called the difference quotient.
Wait, how does it simplify to use h?
Because this is a and this is negative a.
Yeah.
The other reason you can think about it of why it's just h is because, remember, all the numerator and the denominator here is the difference in them, right? So if you take a look back up here, the difference in those two x values is exactly that distance h that we were talking about. So it makes sense visually that this denominator actually simplifies to only h anyway, because it's supposed to be the distance between them. Yeah, it's still just y's over x's. It's the difference in the y's on top, differences in the x on the bottom. So this is the slope of the secant line, okay? Nothing especially different about what's going on there. H could be anything, A could be anything, as long as we're looking at things that are actually defined, right? They actually have values. Now let's take a look at what happens when we talk about the slope of the tangent line. So jot down those pieces of information into your notes. And I would like for you to look at that and tell me what is different between the slope of the tangent line on this screen and the slope of the secant line on the last screen. There's a limit. Very good, Shrika. Yes, there's a limit. That's the only difference, right? The quantity after limit is exactly the same. F of a plus h minus f of a over h. All that's the same. The only difference is this idea of limit. So I'd like for you to imagine what's really happening here on the tangent line. So when we look at the tangent line, what we're actually looking at is we're looking at a line that touches that curve only at that one point. So imagine taking that secant line where it touched at 2 points. And instead of those 2 points actually being 2 points, those 2 points actually are closer and closer to the same point. Can you picture it happening? Those 2 points on the secant line are getting closer and closer together, which means the difference down there in that h value becomes nothing. That's what the limit's doing. The limit is actually making the difference between the 2 points on the secant line become nothing, turn into the same point. That's all that's happening. Okay? Now I want to show you what actually happens in terms of working through a problem with these features. So we're going to take an equation, and if you printed yours out early enough, yours might say g of x down here. Just change it to say f of x so the directions actually just match. So we've got a function, 6 minus x squared. It actually is a parabola very much like the one I drew. And we're asked to do a couple of things. We're asked to find the equation of the tangent line, and then we're asked to graph that tangent line and the original equation later. So those are the two things we're going to do. All right, so an equation of a line. What is an equation of a line that you remember? Like a general form of an equation of a line.
Y equals mx plus
That's one. What's another one that you remember? There's one that's slightly more helpful to us in this situation.
Do you want me to stand with standard form?
Yeah, well, standard form is one that's not real helpful, where it's like ax plus by equals c. That is one too. There's another one, though, that's a little bit more helpful for what we're doing. The point slope form, you got it, Lanisha. Can you tell me what that is? Do you remember?
Y minus y is equal to m times x minus x.
Yes, and both the second y and the second x that you mentioned, we're going to put subscripts of 1 to indicate it's an actual point, a fixed location. So we have y minus y1 equals m times x minus x1. I'm going to use that one simply because it's actually got all the form that we need sort of explicitly defined for us. We actually need 3 pieces of information to use this information in this form. We need an x value and a y value, and we need a slope, right? It's a point slope form. We have one of those pieces of information already given to us. Can you tell which one it is? Nope, we don't have the slope. We're going to have to work for that one. That's the one we're going to work for the most for. We have an x. What's our x value, Blaine?
1.
It's 1. They actually tell you up here x is equal to a, and they tell you the a value is 1. So we actually have the x value in that equation already. How could we find the y value? That's the easy one to find. Plug it into the equation we're given. So I can find the corresponding y value by plugging in the given x value. So f of 1 is going to be 6 minus 1 squared, which is 5. So I have the x value up here, it's 1. I have the y value up here, it's 5. I need to find m. Luckily for you, on the previous screen, I gave you a formula on how to do that, didn't I? There's a way in which we are able to find the slope of the tangent line. And that way in which we do it is this limit definition. Sometimes people will refer to this definition as the limit definition for slope. Okay, so we're going to take a look at using that piece of information, that slope formula, so m of the tangent line, to find this value. So this is the limit. I'm just going to write it on the screen again, so if you don't want to write this piece down, you don't have to. As h goes to 0, of f of a, in fact, our a value is 1, so I'm going to do 1 plus h minus f of 1 over h. And I'm going to show you another way to do this in a minute that does it just a little bit differently, but this is what I'm going to go with on the screen for now. So this is the same definition as the previous screen, except that I know that a is 1. Is everybody good so far? You actually know what f of 1 is as well. We already found it. What is it? It's 5. We found that just a minute ago, right? So as I'm taking a look at simplifying this, I have a minus 5 at the end. How do I find what f of 1 plus h is? I mean, what does that even mean, f of 1 plus h? Okay, let me ask the question differently. How did we find f of 1? We plugged in the 1 in place of x. So, not just the h, the 1 plus h. So f of 1 plus h means plug in the 1 plus h in place of x. So this is the 6 minus, and in place of the x, I'm going to have 1 plus h squared. That's what that function notation means. It means take whatever in parentheses, in this case it's 1 plus h, and replace the variable with that information. So I replaced the variable x with 1 plus h. Is everybody okay so far with that idea? We're doing a lot of replacing in that step. There's a lot of replacing going on. But once I get that piece done, it's algebra to simplify all the quantity that's here. So we're going to use that algebra and we are going to simplify. Now, as we did the limits in the last chapter, we're going to keep writing limit down until I replace the 0 for the h. Why can't I do it now? Because that would put a 0 in the denominator. It's exactly right, Sam. So right now, I have to leave it as is with the limit notation there because I'm not done with it. All right, so now on top, I have 6 minus. Now, 1 plus h squared is not 1 squared plus h squared, right? That's an algebra issue where we have to do something called foiling, or you might have heard of it as distributing. But it isn't just a simple distribution of the squaring, right? It actually means 1 plus h times 1 plus h. So if you multiply that out, you get 1 plus 2h plus h squared. And if you don't remember how to do that, that's something to ask me afterwards. That's something you should remember. And then we have the minus 5 at the end that's still going on there. All right, I'm going to simplify that numerator a little bit more. I now have 6 minus 1 minus 2h minus h squared minus 5 over h. What cancels? The 6, the 1, and the 5, right? 6 minus 1 is 5, and then I've got minus 5, so that's 0. Now notice, everything in the numerator has an h in it, correct? If you do not get to the point in all of these problems where everything in the numerator has an h in it, you have made an error. Because that's the only way that that h in the denominator will reduce with it. Now, there's more than one way to do what I'm about to do next. I'm going to show it to you in the most explicit form, just to make sure nobody cancels things out inappropriately. I'm actually going to factor an h out of the top, which leaves me with negative 2 minus h over the h. And then since it's in factored form, we can actually cancel that h with the h in the denominator. Okay. That leaves me with the limit as h approaches 0 of negative 2 minus h. Can I plug in 0 for h now? Absolutely. What will I get? Negative 2. And what you just found, remember, was the slope of the tangent line. It's the m that we were looking for up here. So I'm able to actually write my tangent line now. It's going to be y minus 5 equals negative 2 times x minus 1. And if you simplify to say y equals, what do you get for y equals? What will that become with a little bit of simplification?
Negative 2x plus 7.
Right, negative 2x plus 7. What we've done is we've done the first part that's underlined in green. We've found an equation of the tangent line to our function at the point x equal 1, actually. Next, we're going to graph. What are we going to graph? Well, we're going to graph the function we were given originally, right up here, f of x equals 6 minus x squared, and we're going to graph the tangent line that we just got. So take your calculator, and I want you to graph the function and the tangent line. If you put it in a standard window, all of our windows will look pretty much the same. That would be zoom 6 on the 83s and 84s, which will put it in a standard 10 by 10 window. Well, negative 10 to 10, it's actually a 20 by 20 window. Okay, so the general shape of the first equation is a parabola opening how? It opens down, and it actually has a maximum value on the x-axis. So it looks something like this, right? And the point x equal 1, y equal 5 would have actually been over here on your graph, 1, 5. And you should see a line going through that point when you graphed your other one that looks, that's not a very good example. Let's try that one. That's a little bit better. They look something like that. Did everybody's picture look like that? Now, this doesn't prove that you did it right, but looking at it tells you that it seems reasonable, right? It looks reasonably good. It looks like it's a reasonable solution. If you saw this graph and the line looked like that, you would say, oh dear, I did something wrong. Definitely have the wrong slope for sure. Something's going on. It's weird. So that's the kind of thing you're looking for. This is almost like a check step to see, is my answer reasonable? Okay, so any questions on this one? Okay, go back to the section title. What did the section title say we're going to do in this chapter, in this section of the chapter? Tangent lines and velocity. So we've talked about the tangent lines. Next, we're going to talk about the velocity. So this is the definition of instantaneous velocity. Instantaneous means it happens right now, right? It happens in an instant. It's the speed that your speedometer says on your car when you look on the car's speed. So average velocity would be like your speed over time. This is actually the speed right now when you're driving your car and you look down. So we've got a position equation, S of t, that just tells you where something is. So it's the position where something's located. And it's located at a specific point in time. And our object is moving somehow, and this instantaneous velocity is the speed, actually, that it's moving. So this would be like somebody calling you on the phone and them saying, where are you and how fast are you going, right? Okay, well, I'm located at the Loves on the side of the road of this particular point of the highway. How fast am I going? Well, if you're stopped, you'd be going 0. That'd be your instantaneous velocity. If you're driving, you would be going a certain speed. Now, I keep using the word speed. Speed and velocity aren't exactly the same thing. Speed is actually the absolute value of velocity. So when we talk about speed, our speed is always a positive value, right? But the direction in which you're going really matters on whether or not you're arriving at the right place. Yeah? So if I'm on my way to school and my husband says, where are you? And I say, I'm at the Loves, but I'm going the wrong direction, I'm not going to arrive at school on time. So what velocity actually does is it actually takes into consideration a positive or a negative value depending on the direction you're moving. Okay, so negative would be something where you are going the opposite direction of whatever is considered a direction you're intending to go. It depends on the context. But what do you notice about this definition right here, this V of A? That's the same definition that we saw a little while ago, isn't it? It even simplified the denominator the same way. It's a limit. It's the function value with the a plus h in it minus the function value with the a in it divided by h. It's the same thing. Even with the limit, it's the same piece. So this is actually the same question. So when we're asked to find slope and when we're asked to find velocity, we're asked to find the same thing. So let's take an example, and I'm actually going to show you how to do this problem a little bit differently than the last one. Now, taking a look at this one, you notice one thing, of course, is that it's got a denominator, which means things are going to be treated a little bit differently. That's really not going to affect the beginning of the problem. However, what else do you notice that's different about this? It has two a values. So think back with me to this problem we did before over here. If I do the problem exactly like this is set up, I will have to do the problem twice, right? I don't know about you, but I don't like to do things twice if I can do them once. Do you? So I'm going to show you how we can do it once and use that information to make a decision about the second piece. So the way that we do that is instead of actually finding that 1 plus h like we did before, we are going to leave the a in the formula. So we're going to find v of a, which is the limit. I'm just writing down what we're actually finding now, as h goes to 0, of s of a plus h minus s of a over h. That is the definition of what we're doing here, right? Okay, so let's start with that s of a plus h. The s formula is right here. It's s of t. What do I do with a plus h to find s of a plus h? What did I do when I found, if I were to find s of 1? Okay, how, Sam? Or where? For the x's, yes. So in place of where the x is, I would write the number 1, right? So s of a plus h means in place of where the x is, I'm going to write the value a plus h. So I'm going to have the number 2 over a plus h plus 1. I'm sorry, I left my limit off. Let me put that in there real quick. You guys don't leave yours off. Okay, this quantity, 2 over a plus h plus 1, is the value s of a plus h. It's the a plus h plugged into the function in place of x. Using that same idea, what would s of a be? 2 over a plus 1. That's exactly right. So minus 2 over a plus 1. In place of where x is, I substituted in the value a. And this is written all over the quantity h. You'll become more comfortable with the notations the more you use them, I promise. But they're doing the same thing we do with numbers. You're just doing it with letters. You're replacing the variable, wherever it is in the equation, for a quantity. In this case, it's the quantity a or the quantity a plus h. Now, just like on the last problem, I can't plug 0 in for h. That's the problem here, right? That is the problem. So somehow we have to do some sort of simplification to allow that h that's in the denominator to reduce, to simplify, to go away. So as you're taking a look at this, thinking about some algebra skills you know, what would be reasonable to try?
Common denominator.
Right.
Numerator.
You got it. Somehow we got to get those two fractions to combine. And the way we combine those fractions is by having a common denominator. Okay? Now, they aren't especially, helpful looking. They don't look like the fractions that you've seen all of your life, right? We don't usually use fractions that have what appears to be 2 letters in the denominator. That's a little different. But it works the same way. Because the a plus h plus 1 and the a plus 1 don't have any factors in common, they have terms in common. Remember, terms are the things separated by the addition and subtraction. Factors are actually being able to do it in parentheses and it's a multiplication factor. We don't have any of the factors in common. So the common denominator is just going to be the 2 denominators multiplied together. So our first actual step of algebra is to actually rewrite this as a common denominator. So we're going to have 2 times a plus 1 minus the 2 times a plus h plus 1 over the whole denominator, a plus h plus 1 times a plus 1. So in other words, let me write it in over here. This one got multiplied by a plus 1 on top and bottom, and this one got multiplied by a plus h plus 1 on top and bottom. And instead of writing this as all over h, or division by h is the same as multiplication by 1 over h. So I'm going to write it as multiplication so that I can get rid of this double fraction look. Does that make sense? This one up here said divide by h, so I've written multiply by 1 over h. Okay, is everybody good to move on? Okay. We have a lot of simplifying still to do, but is the setup okay? All right. Let's simplify that numerator. Let's distribute. Let's multiply things out. So I have the limit as h approaches 0 of 2a plus 2 minus 2a minus 2h minus 2 over a plus h plus 1 times a plus 1 times h. What happens? Stuff cancels, that's exactly right. Which is what we're going for, right? What stuff cancels? 2a and 2's. So what's actually left on top? Negative 2h. So everything that's left on top, and it's not very much on this one, has an h in it, right? Okay, good. Excuse me. All right, so on top now, we still have that limit as h goes to 0. I'm running out of space, so I'm going to try and squeeze it in over here. I have negative 2h over a plus h plus 1 times a plus 1 times h. Now what? This is factored now, right? Everything's written as multiplication pieces. So what reduces? The h on top with the single h on bottom, right? And if you'll think back to that test that we just looked at beforehand, this is essentially what happened on that one problem, right? That we were looking at that ended up with the 3x on top and the x on bottom and the x's canceled. Same's happening here, right? All right, so good, good, good. And so are we able to now plug in the 0 for the h? You betcha. So let me write one more step before I plug it in just to show it. I've actually got negative 2 on top. I have a plus h plus 1, and I have a plus 1 on bottom. So if I plug in 0 for h, what do I get? Negative 2, and then what? So could I write it as a plus 1 squared, Ben? Yes, I could. Right, so this h right here being a 0 leaves me with a plus 1 here and another a plus 1. So this is a plus 1 squared. Exactly. Now, see, this what I've found is I found a formula for velocity. Velocity in terms of a. And so, Hunter's exactly right. Now I can actually just find the one I want. So I can find v of 1, because one of the quantities I was supposed to find was a equal 1. So I can plug in the number 1. So this is the number negative 2 over 1 plus 1 squared. What will that become? It will become negative 1/2, yes. And I can find v of 2 without doing the process over again. That's big time important, isn't it? I just cut your workload in half by showing you that trick. It's not really a trick, but in some sense, if you're not aware of it, yeah, I mean, you would have had to do twice as much work. So if I plug in now the negative, or the 2, I've got negative 2 over 2 plus 1 squared. And what do I get? Negative 2/9. Okay, is everything okay on this? All right, I want you to get out something that you can use as a straight edge. What I want you to, so maybe an ID, maybe it's your calculator lid, maybe it's just a fairly sturdy sheet of paper that you have. But grab something that you can use to draw against that would be able to make a straight line, okay? What we're going to do in the last part of this little lesson is we're going to actually talk about how we sketch or think about plausible tangent lines. Now, I will say that unfortunately, I tried my best and I couldn't figure out how to make Word do what I wanted and put points on your graph. So none of our points are going to be precise, but I want you to put the A value pretty close to here, the B value at the very top of the curve, C over here fairly close to C, and D over here fairly close to D. I know nothing was exact about what I just said, except for B is at the very top of the curve. That's important. So put those 4 dots in there. And then what we're going to do is we're going to sketch what's called plausible tangent lines. We're not finding an exact here. We're sort of doing kind of like what we did on that first one where we looked at the graph and said, that looks reasonable. We're sketching something that looks reasonable. So the way that you do this is you take, you take your straight edge at the point A, and you line it up nearby to the point A so that it looks like you're very barely touching the curve. But you're supposed to be sort of equal, so you're not trying to barely touch the curve and be really slanted top or really slanted to the edge down here. You're supposed to be trying to equally approximate it to both sides of the curve where it is. So something like that. Are you guys with me? So this is one of those things that if I'm assessing it, if I'm grading it, I can tell you when you screwed it up totally, right? Because it looks wrong. But there's lots of things that could look reasonably right. They don't have to be exact. So your tangent line on A looks something like this. Now, the tangent lines we're drawing a lot of straight lines here because I wanted to use the same picture for all four of these values. So our tangent lines are going to cross each other. That's not of any kind of importance at all. Think about with me now what happens when you have the point B, however. B is at the top of the curve. What will your tangent line look like if you're doing the point at B? It can't look like this because then it's not anywhere close to the curve over here. And it couldn't look like this because then it's not anywhere close to the curve over here. Okay, don't use the word straight. Try another word. Horizontal, yes. So when we're actually at that peak of the curve, and it would be the same thing if we were at the valley down here at the bottom, between C and D, we actually have a horizontal tangent line. So I'll change my color just to identify it differently. But it looks something like that. Now C is drawn in such a way that if you were to approximate that, your line's actually going to look like it's doing what? It's going to kind of look like it's just part of the graph for a little while. But if you go far enough out on your tangent line, it's actually going to look like it's cutting through the curve too, doesn't it? Like that doesn't normally happen. If you take a look back over here at A, you are strictly on one side of the curve. You do not cut through the curve. But because of the location of C, or the approximate location, it is reasonable as we draw this for it to actually look like it's cutting through the curve. That's not good. Let's try again. Okay, this is not fabulous, but it's pretty close with my screen. So it looks like it's really hugging the curve on both sides, but eventually, as it continues to hug the curve on the top part actually starts curving back downwards, right? It does curve, whereas your line keeps going straight, so now it's above the curve on the top, and it looks like it's going to be below the curve on the bottom. And point D, I think you probably can draw point D in without too much trouble. Point D looks something like that.
What determines which side of the line it goes on?
Part of it is the straight part of the edge. For instance, if you tried to draw part D on this side right here, like this, you wouldn't be able to. It would cut through. It's really steep, so it's hard to see that. But when you line it up, it's got to actually be on the curving side of what's going on. The side that's actually got the curve to it. That's where it's the curving on the outward part. Otherwise, the line just won't line up right. Yeah. The other part of this question, so it said to sketch plausible tangent lines. It also said list the points in order of increasing slope. Okay, so let's look at those lines we drew and think about what slopes you're seeing. What can you tell me about the slope at point A? It's positive, good. Is there any other slopes that are positive? D. Which one is more positive? D, because it's steeper, right? It's a steeper part of a line. That brownish line I drew is actually steeper. What about point B? It is a y equals something. Y equals like a constant. What about its slope? It's 0. It's a slope of 0. When something's flat, we talk about having a slope of 0. Don't say no slope. That's inappropriate. That's what we actually mean when something's a vertical line. But it's a slope of 0. What about C? That slope is negative. So if we're going to put them in order, which one should come first? C, because it is negative. What would be next? B because it's 0, and then A, and finally D because it is the steepest positive slope that we have. All right, any question on that? Now, this next piece right here, I could have put inside of this section or inside of section 2.2. It doesn't really matter. It comes up a little bit in both of them. It talks about places where tangent lines don't exist. So if you were to draw a tangent line everywhere on this graph over here, we had a tangent line to draw. That was just fine. But there are actually 3 types of descriptions of where tangent lines don't exist. The first one's discontinuities. Now, we've talked about discontinuities before. Tell me what kinds of discontinuities we've seen. Holes, asymptotes, there's one more, jumps. So if the graph has a place where the graph jumps, or a hole is left out, a point is left out with a hole, or it has an asymptote, you're not going to have a tangent line there. It's not going to be possible to draw it. Sharp turns is an interesting one. So a sharp turn would look something like this. If I were to draw a tangent line, this is an interesting one. Let's say I tried to draw a tangent line at this point right here. What would the tangent line actually look like? The line itself, right? Yeah, it would have. And the same thing over here on the right-hand side, right? The tangent line is actually that line itself. The problem is up here at the top, there's no way to get close to those 2 tangent lines, right? They are completely different. One tangent line is positive, the other tangent line is negative, and even if I tried to do something like this as a tangent line, I'm nowhere near either of the original tangent lines. So if I've got a sharp turn, that is if the graph is not smooth in one point, it has a sharp point to it, it won't exist at that one point. The last one's vertical tangent lines, which is an interesting one as well. So this is a graph where it looks something like this. You don't see them too often, but I bring them up because they are a legitimate issue. If you took the particular point right there in the middle and you drew a tangent line, what would it look like? A vertical line. The problem is with a vertical line, the slope doesn't exist. I mentioned it just a minute ago. And so we can't talk about that limit definition because that limit definition hinges on the fact that a slope does exist. There is a no slope or a does not exist type of a slope when you have a vertical tangent line here. This one rarely ever comes up, but you should be aware of it if you do see it. You would see it mostly in terms of a picture given to you, not an equation given to you. All right.